Part 8.3, Efficiency Analysis for Mergesort. In this part, let us do the efficiency analysis. Now, first, let us derive recurrence relation for the Mergesort. Let us just use a diagram. We can easily see the recurrence relation. For the Mergesort, actually, our main focus is on the worst case. Why? Because when we design this algorithm, our consideration is we want to make the worst case efficiency as best as we can. For that reason, when we do divide and conquer, we split our given data into two evenly distributed two subarrays. Two subarrays with almost the same size. So by balancing principle. For that reason, we can expect the worst case efficiency should be pretty good. All right, so let us do the analysis. So this is the whole array, and we use a function t of n to represent the number of comparisons. Then we split in the middle to get two subarrays with almost the same size. So now if we estimate the number of comparisons for each subarray, so we can use t of n over 2 approximately. The second one also same expression. But then we need to do the merge, right? After the split, then we call recursive function and get each subproblem solved. But at the end, we need to merge two subarrays. So what is the total cost? So look at the total size, and we use the formula. So we have the formula for the worst case and for the best case, right? Formula for the worst case, the general case, the total number of elements minus 1, right? Here, total number of elements n minus 1. So there is a minus 1, right? But the minus 1, it is very close to n. So we just use n. The reason is after we drop that minus 1, we can make the equation simpler, but very close to the original one. So for that reason, we get a current version recurrence relation like this one. Next, we want to solve it. All right. So we consider simpler case. Because to solve this recurrence relation, it may not be that easy, right? So we want to start with n equals power of 2. In this case, we get the easiest possible expressions. All right, so let's plug in so we can get this new recurrence relation. You can see inside the parenthesis, we have a power of 2 expression. Now, let us do the transform and try to get a better view of the recurrence relation. But how to do it? There is another commonly used method called a division method. How do you know you should use the division method? Usually by experience. You examine the structure of the current equation, the structure. So you should get some sense. If you have a lot of experience, you should get some sense. If we do division, both sides, power of 2 to the kth power, so you will see we get a new recurrence relation, but this time, this new recurrence relation will expose structure better. Expose structure better. Yeah. So can you see the similar structures? These two fractions, do they have similar structure? If you can see, then we're almost there. Yeah. Because you can see they have the similar structures. Yeah. The only difference, you just change the superscript from k to k minus 1. That's the only difference. Yeah. All right, so next, we want to solve this new recurrence relation. Yeah, but we want to get a better view of it. Let's take a look. Yeah. We like to define a new function. New function. Why you want to introduce a new function? The reason is we want to get a better view. Yeah. So how to introduce new function? Yeah, pretty straightforward. Just to define a new function as that fraction expression. G of k. G of k equals that whole fraction expression. All right. After that new notation, yeah, let us rewrite the original recurrence relation. What shall we get? Yeah. The new equation we will get g of k equals g of k minus 1 plus 1. And initial value g of 1 equals 1/2. Is that much simpler? You just look at the new recurrence relation. If you compare with the old one, do you feel it is much simpler? Yeah, no problem, much simpler. Then we try to solve it. We can solve it directly. Yeah, let us write another iteration. All right, substitution iteration. All right, you can see we will get g of k minus 2 parentheses plus constant term 2. You can see we reduce the variable by 1. Yeah, here you increase the constant term number by 1 also. All right, so let us keep doing in this way, but we want to keep track of this property. Can we keep track of it? Here, use one special method I mentioned before. Yeah, here, let me just recall this method. Invariant. Here, if you can observe, there is some invariant. So how do you get that? The size number k minus 1 plus the constant term 1 equals k, right? The size number k minus 2 plus the constant term 2 equals k. That sum is invariant. For all equations you write out, that number is invariant. Now you want to write the last expression. Inside the parentheses, you want 1, g of 1. That's the base case, right? G of 1. But what is the constant term? Right? The constant term, k minus 1. Why? Because you know, based on the invariant property, 1 plus the constant term should equal to k. So that's the reason the constant term must be k minus 1. All right. Now we have the final expression. Yeah, because g of 1 equals 1/2. Yeah. So the g of k equals k minus 1/2. How simple it is, right? How simple it is. Yeah. Yeah. But we need to go back to the original function expression, t function, not g function, t function. Yeah. So let us go back. Yeah. Let us start here. T of 2 to the kth over 2 to the kth equals k minus 1/2. Yeah. Then t of 2 to the kth equals parenthesis k minus 1/2 times 2 to the kth. Yeah. But we want to go back to the original variable n, not a k, in terms of n, not in terms of k. All right, yeah. So here we can represent k as log base 2 of n. Log base 2 of n, okay, yeah. So then you can see t of n is approximately, because we dropped that 1/2, okay, minus 1/2. K corresponds to log base 2 of n, and that 2 to the kth, that is n. N log n. All right. Yeah. So if you want to use the asymptotic notation, you can write big theta of n log n. Okay. Yeah. N log n. That's the reason we have this worst case efficiency for merge sort, n log n. Big theta of n log n. All right. Yeah. But at the end, I like to mention a little bit, yeah, for merge sort. Although we may not do it here, but I just let you know these three cases: best case, worst case, average case, all right, or big theta of n log n. The reason is pretty simple, because we make the even split. Even split would give us best worst case. So the best worst case, not too bad, right? Not very bad. So, and not much far away from the best case. All right? Yeah. So that's pretty reasonable. The best case, worst case, average case, yeah, they all fall in the same asymptotic notation category, n log n. Yeah. All right. So that is the 8.3. Yeah. So for the last one, 8.4, I like to do a simple example. So let you get a better understanding when we apply the merge sort. So what is the details when we apply the merge sort? All right, so let's finish.